All right, good morning, everybody. Today we're going to make this one pretty quick, just so that we can get through it. It's Friday, April 17th, and for some reason it is snowing. I have never seen snow this late in April, but hey, first time for everything, I guess. All right, so we're going to go through population dynamics. This is kind of a follow-up to when we went through ecology. So this is kind of a part two for that. So our outline, we're going to look at how populations actually grow, the different conditions that are kind of behind their growth, why they happen the way they do. And then a lot of that is going to focus on exponential versus arithmetic growth. Also Malthusian versus logistical growth. We're going to look at population increase, population decrease, survivorship rates and survivorship curves, age structure within populations, regulating population growth, and density dependent versus density independent factors for population growth. So getting into our first thing, we're going to look at dynamics of population growth. So exponential growth is growth at a constant rate of increase per unit time. It says geometric growth. I've never seen anyone refer to this as geometric growth, but it is this exponential scale that is right here. So as you could see at first, yes, it does have a slower increase than arithmetic growth, but at the same time, once it hits a certain point, then it overtakes it and then opens that gap up quite largely compared to arithmetic growth, which is where it's at a constant rate. If you measure the slope of this line, it is extremely constant, while the slope of the exponential growth is will constantly be changing throughout that curve. So looking at exponential growth, this is where the number of individuals added to a population at the beginning of the exponential growth is relatively small, but the number increases quickly as the population and thus the given percentage of the population grows. So what you're doing in this case is it's multiplicative growth, as in you are multiplying by a number. So a doubling of the population compared to arithmetic growth, where it is adding a set number of individuals every single time. So I'm going to be adding 100 to the population versus I'm going to be increasing the population by 2%. So this leads to this J-shaped curve, your typical exponential curve. And so one of the things that we look at when we measure this is doubling time, which is how long it takes for a population to double. So it's 70 divided by annual percentage growth rate. Biotic potential is the maximum reproductive rate of any organism. All right, so if you were to measure how many offspring that organism can give off over its lifetime. So looking at this, with biotic potential, you should end up with this curve. This isn't going to be perfectly vertical. It will have a slight taper, since you can't have any 2 points of a line located up on a vertical axis like this. But you will have this kind of jump where each organism in the beginning is contributing its maximum, and then once enough organisms start to hit maturity and they each contribute their maximum, you're going to have this massive jump in population. Now compare that to what we actually see, which is this S curve. And this environmental resistance is death, disease, predation, anything like that that is going to limit how many offspring an actual organism can have. We know that hypothetically, okay, so humans, let's say they can have, hypothetically, a child every 9 months. Does that actually happen? No. And it assumes that they will have a child from the time that they're reproductively viable all the way up to the time that they're not. And during that period, the only thing that they're focused on is just having children. So you end up with these kind of jumps in growth rate. Compare that to the environmental resistance. This is actually what happens. And there is a theoretical maximum, your carrying capacity. This is how many individuals can survive within an environment based off of factors that will limit that infinite growth. So you end up with these oscillations in population. So the first thing you have is you have this overshoot, and this is the measure of the extent to which the population exceeds carrying capacity. So what happens when it exceeds carrying capacity? Well, some of those individuals that are above the curve will not survive. So then you have dieback, which is this negative growth from not having enough of something which defines your carrying capacity. It can be food, space, water, any sort of resource. So the severity of the dieback is generally related to the extent of the overshoot, and we'll see a graph of that. So you can see here, you have this population, it grows, and notice how much higher over this line it goes. This right here is going to be the extent of your dieback. So why does it continue like this? Because not all individuals that are over this are going to die. Some of them are going to be left into a weakened state. So even when you drop below carrying capacity, there's still these individuals that are in a weakened state. And then eventually the population will start to climb. And notice that your level of overshoot in this range is a little bit different. And because of that, your level of dieback is a lot different. And then that kind of continues on in this decreasing oscillation. Will it eventually theoretically get to the carrying capacity of the environment? Yes, theoretically it should. Do we ever see that? No. There are instances where it gets pretty close to it, but you will see slight fluctuations. Why is it that you'll never see a population ride carrying capacity like that? Because carrying capacity is never a set stable value. It's always changing, it's always increasing and decreasing based off of what is actually happening within the environment. So looking at Malthusian growth, this is also called interruptive growth or eruptive growth. So population explosion followed by population crashes. So it's concluded, or Malthus concluded that human populations tend to grow until they've exhausted their resources and then crash. Notice human populations. There's the garbage trucks are in the background. So notice this says human populations. So this goes to the point where it will continue to grow until all resources have been exhausted, and then there will be a crash, just like what we saw in the previous graph. Logistic growth. So logistic growth rates that are regulated by internal and external factors until they come into equilibrium with environmental resources. Again, this is theoretical. Why is it theoretical? Because these environmental resources are constantly changing. There's a constant increase or decrease. So growth rates slow as populations approach carrying capacity, and it leads to that S-shaped curve that you saw in the first graph, or the second graph. I'm sorry. The first graph showed the difference between exponential and linear growth. So environmental resistance, which we saw in the second graph with the J versus S-shaped curve, is any environmental factor that reduces population growth. So chaotic versus catastrophic dynamics. So chaotic systems exhibit variability and complex pattern, not observable under normal human scales, as in these usually take a very long amount of time. So this was observed by Edward Lorenz, called the butterfly effect. So it either occurs over a very long amount of time, or it's at such a small micro scale that it's difficult for us to investigate. We see the effect, but the cause was something that was very tiny. If you've ever heard of chaos theory relies on that it's not one large incident that causes a problem, that it tends to be a result of a lot of smaller problems that add up and stack up and lead to one gigantic thing that happens. Compared to catastrophic systems, where it may jump from one steady state to another without any intermediate stages. So this is balancing a chair on 2 legs. Notice it goes from 4 to 2 without going on to 3 legs. So looking at Malthusian strategies, you're going to have a short life, rapid growth, early maturity, maturity being the ability to produce viable offsprings. There's many small offsprings. There's little parental care, meaning that once an offspring is born, that most likely there's going to be a limited amount of input from the parents before that organism goes out and starts living its life. There's a little investment in individual offspring themselves. So rather than focusing on individuals, you tend to focus on the best outcome for the group. They are adapted to unstable environments. They're pioneers and colonizers. They are the first ones in. They tend to get in when there's very little competition. They are very niche generalists. They have nobody else that kind of competes with them because they have this specific thing that they do. Most likely they're prey, just because of the fact that they're going to be small. There's going to be a lot of them with rapid growth, early maturity, and little parental care. And they're going to be regulated mainly by extrinsic factors. They're going to be pretty low on the trophic level, which is kind of inherent in saying that they're prey. So looking at logistic strategies, they tend to have long lives. They're slow growers. They tend to have maturity a little bit later in life. Instead of having many small offspring, you have fewer large offspring. There's high parental care and protection. There is a high investment in individual offspring. They're adapted to a more stable environment. They tend to be in later stages of succession, later on down the line, where there is a little bit more competition that they can thrive in. Tend to be niche specialists. They're more predators, and because of that, they're higher up on the trophic scale, regulated mainly by intrinsic factors. And like I said, they're higher up on your trophic levels. So factors increasing or decreasing populations is natility, which is the production of new individuals, compared to fecundity, which is the physical ability to reproduce. Fertility is the measure of the actual number of offspring produced. Immigration is new organisms introduced into the ecosystem. And then, of course, with population decrease, you have mortality, which is your death rate. So for survivorship is the percentage of cohorts surviving to a certain age. Life expectancy is the probable number of years of survival of an individual of a given age. If you look up, like, for instance, human life expectancy, that is based off of the averages for individuals. Increases as humans age, and then a lifespan is the longest period of life and that can be reached by a given type of organism. So this would be comparing how old does the average individual live versus how old does the longest person live. And then emigration is when you have individuals leave a population. They move out and they are removed from that equation. So looking at survivorship curves, there's 4 general patterns. For the most part, there's really 3 that are covered in depth. There's full physiological lifespan, probability of death unrelated to age, mortality peaks both early and late in life, mortality peaks early in life. So here are your survivorship curves. The ones you're going to see most common are A, B, and D. C is rarely ever seen. But A is where you have very few individuals. They tend to live very long, and then you tend to see a drop off of them as they hit post-reproductive age. Compare that to D, the exact opposite, where you have this sharp decline in this younger period, and then they make it to the reproductive period, and then the rest of them are kind of taken out in the post-reproductive period. With B, you just tend to see a steady decrease in the number of individuals as age increases. So you could think of the x-axis as age. So as you get that, you tend to get more of a decrease in individual. And then C, like I said, you will rarely ever see this, but it is a sharp decrease in the dependency period, flattens out quite a bit in the reproductive period, and then post-reproductive, it crashes just like the rest of them. So age structure. Growing or declining populations usually have very different proportions of individuals in various age classes. So as we saw in the last one, you're going to end up with this wide distribution of where people are or ages are located at. So rapidly expanding populations have a large number of pre-reproductive individuals and thus have population momentum. That doesn't mean that they're currently expanding. It means if you look, you're going to have more of your individuals going off of those three chunks, the pre-reproductive, reproductive, and post-reproductive. You're going to have a lot in that pre-reproductive, which means that as they start to age up into that reproductive age, again, population momentum, you're going to have a lot of individuals that are capable of having children, which means even if you just have replacement, you still have a population growth because that chart is starting to shift upwards. The diagrams will show a very, very large base. So stationary populations is when you have your ins equal your outs, the amount that think of it as a math equation, the number of births and immigration equals the number of deaths and emigration. So it's where everything is equal in that population. There are no bulges in the diagram. It tends to be pretty straight up. There will be some diminish as you get higher, but fertility has fallen below replacement levels in diminishing populations. So this is, rather than one individual having one offspring, this is where it tends to fall below 1. So you have negative population growth. So diagrams show a bulge in the upper age classes and then kind of a decrease in those lower ones. So this is what you will look, what I was talking about with those diagrams. You can look these up on the US Census website. These are your expanding populations with males on left, females on right, and then the youngest are at the bottom and the oldest are at the top. So you can see in this diagram that you have fewer people in the post-reproductive ages. Then you have even more in the reproductive ages, and then even more than that in the pre-reproductive ages. So thinking about this over time, this section right here is going to move up and then move up, and it's going to continue up. Will it decrease a little bit? Yes, because not all are going to survive to make it to reproductive ages, but for the most part, you can see how large this is, and it's going to be moving up quite a bit. Compare that to a stable population. You tend to see this a lot more in developing countries. So this is where it remains pretty stable. Mostly you're paying attention to the reproductive and below. So looking at these, this tends to be pretty stable. There's not really any bulges. You end up with the same little pinch off at the top. And then diminishing populations, this is where there are fewer individuals the younger you get. So you have to think that this category right here isn't going to grow any larger as it moves up to here and up to here. If anything, it will decrease due to mortality factors. Regulating population growth. So intrinsic factors, which we had talked about earlier, operating within or between individual organisms of the same species, compared to extrinsic factors where it's imposed from outside of the population. And then biotic is caused by anything living. Think of bio as living, compared to abiotic. Think of abio, a meaning without. So that's caused by non-living environmental components. So if I say name environment or name biotic and abiotic components of your property, like the sidewalk, because it's made out of concrete, would be abiotic. Biotic would be things that are made out of, or like plants, anything living on your property. Density independent factors. So these are things that regulate populations. So constant proportion of the population is affected regardless of population density. So this can be, so these are things where if you add more people to it, it doesn't matter because that proportion is going to be affected. So think about the situation that I was always told is, let's say it starts raining and during this storm, one person gets hit by lightning. every single time there's a storm, one person gets hit by lightning and they end up dying. Doesn't matter if you have 1 or 100 individuals. No, there's still going to be one person that gets hit by lightning because those are the factors that are set up in this hypothetical. So these tend to be abiotic components. They don't directly regulate population size because a lot of times they tend to be pretty random. Compare that to density dependent factors. This is where more of the population is affected as the population increases. These tend to reduce population sizes by decreasing natality and increasing mortality as population size increases. So you could think of interspecific interactions, so predator-prey oscillations, or intraspecific interactions like territoriality, stress-related diseases. In bio, right before we left out, even though we had talked about this earlier, one of the bio students asked, is China going to be more affected by coronavirus because there's more people? The answer is yes, because of the density. They have, they're the biggest country in the world, and they have a lot of people centered in very, very large cities: Hong Kong, Beijing, Shanghai, Shenzhen. And because of that, once it ends up there, the portions of people that are going to end up getting infected with it tend to increase. Think about high-speed trains that you see in Asian countries, how they just literally push individuals inside of trains. Now, what if one dude in there has coronavirus or any other disease that can be transmitted through physical contact or airborne? You have introduced a density-dependent disease into a high density area. Therefore, it's going to jump to more individuals. So this goes back to social distancing. Why are we doing social distancing? Well, because what we're doing is we're artificially reducing high density areas. So for instance, why are we not in school right now? Well, because we have, 1,900 plus students at school plus 100 staff members or more. And so by telling everybody stay home, then we have instantly reduced the population of that down. Stores closing. So for instance, saying the mall is a high density area. And by closing it, we are reducing the amount of people that are in there, therefore decreasing the possibilities of disease moving around. This can also be food. So think about, I used to bring in donuts every Friday. What if I only brought in, we had 22 students in class. What if I only brought in 22 donuts? Well, every person's going to get one. But what if I only brought in 20 donuts? Well, then having 22 students is a problem because not everyone is going to get one. What happens if I only bring in 10? What happens if I bring in 22, but someone decides to sneak one before class? What happens if people don't show up? So instantly you're varying the population of this environment and the density of this environment, and you're changing how those resources are distributed. So to summarize this, I told you it'd be a quick lesson. We looked at dynamics of population growth, exponential versus arithmetic. So exponential versus linear, Malthusian versus logistic growth. We looked at what causes populations to increase and decrease. Survivorship curves, 4 survivorship curves, 3 that you're going to see for the most part, and 1 that you'll almost never see. We get age structure, regulating population growth, like what out there regulates it, and then density dependent versus density independent factors. Told you this was going to be a very quick lesson. I wanted to make it really fast. It's Friday. It's snowing outside. I don't think anyone is having a great day today just because of those two things, coinciding. Being a Friday is awesome. Having it snow can be awesome. Having it snow on a Friday in April is not exactly an ideal day. I'm going to be moving over to Google Meet in just a moment. So that will give you an opportunity to ask questions. I'll be over there until 11 o'clock. A couple things I wanted to go through. Before we end, we'll switch to the camera. A couple things I wanted to go through. All right. First thing, if you know of people who have not got a hold of their first period teachers and told them about whether they have a computer or not, let them know. Make sure that they are getting a hold of their first period teachers. If you know of people who are not logging on to PowerSchool, tell them they need to log on to PowerSchool. All right, you have to get on to PowerSchool so that we can, so that you can do assignments and things like that. Email assignments. If you know of students who have not contacted their teachers, even if it's just one teacher, have them do that. All right, grades can only go up from here, so make sure that you guys are putting in the work that you need in order to have your grade increase. What else? Stay up to date on everything. When you email or with assignments and things like that, use your school email account. You can link your school email account to your phone. You can also tell your phone, I only want to get emails during school hours. That way you're not getting flooded with emails on weekends and stuff like that. But make sure that you are kind of staying up to date on everything. Check your school email. If you send us an email, send it through your school email, because a friend of mine had an email address that was ridiculously stupid, and every time he would send me an email, it would automatically go to my junk inbox. All right, I might do a video separate, not on this channel, of how to actually send an email to a teacher, because it's amazing the stuff that I've received. If you have questions about anything, email us. We are here to answer all of those questions. And we want to help out as much as we can. Stay up to date on stuff. I know for some of you, you think that you're done for the year, but the year is not over. We are still moving forward. School is still in session, and I know for some of you, you never attended when you were there, but make sure that you're still actually keeping up to date with the work. Get a hold of everybody, make sure they're doing everything that they need to do in order to be successful in class. Because remember, we have an AP exam in a month. All right, we have an AP exam in a month. So make sure that you guys are doing everything that you need to do to prepare for that. I know some of you aren't taking the AP exam, but at the same time, when you go on, I used to teach it to universities. So when you go on to another university and you don't know anything about environmental science, they're going to be like, who is your teacher? And you say my name, that's not going to look good, because of the fact that I know that I'm doing everything that I can in order to help out. So make sure that you guys are checking your emails, make sure that you're staying in touch with your teachers, make sure you're doing everything that you need to do. I'm filling you guys in on information that I have as it's going. So if you have any questions, if you have any complaints, any issues, whatever, send me an email or show up to Google Meets. For some reason, I sit in office hours. I had 2 hours of office hours yesterday, and I sat there by myself for 2 hours. Show up to those things. They're only going to benefit you. All right. That's the end of my rant. Enjoy your guys' Friday. I know that the weather out there sucks, but you guys have a good rest of your day.